Hello, welcome. My name is Stephen Ng. I'll be representing Team 7, Plasma. Our project was the construction of a microwave plasma reactor for the synthesis of nanomaterials. Our advisors are Dr. Svetlana Naratina and Dr. Robert Hughes. Our team overview, we have Zach Eskin, who is our SD1 team leader. I am the Senior Design 2 team leader. Jason Martin was in charge of the apparatus design, and Matt Bruns is our safety manager. The purpose of this project is to create noble metal nanostructures through a microwave plasma reactor. This abstract basically goes through how we are creating it and its purpose. The current technology that is currently being used is the tube furnace. It takes about 4 to 6 hours for the tube furnace to de-wet nanostructures. Through this, it takes about 30 minutes to the de-wetting process to initiate, and there's a lot of heat loss. Our proposed technology is the microwave plasma reactor, in which we will concentrate the heat. The fabrication time will be about 5 minutes, and it will be less than a minute to de-wet. So this is our proposed solution in a system block diagram. We first had to start off by choosing a gas to create plasma in the microwave. We chose the inert gas of argon because it's non-reactive. It will not react with our samples, and also was readily available and inexpensive. From there, we were able to test the plasma creation in the microwave. After that, we were able to design our quartz reaction chamber with the help of David Plaskett of the Bury Chemistry Department. From there, we were able to draft our gas handling system, in which we were able to keep the diameters of our pipes about the same. Once we ordered the fittings for the system, we were able to put it together to sustain plasma. Once we were able to hold a sustained plasma with our prototype, we were able to test if we could de-wet a sample. From the test, we were able to validate. So far, we only have optical spectroscopy. Unfortunately, the SEM machine at Westchester was down yesterday, so we were not able to get a sample for us. We moved on from the prototype. We made adjustments based off the prototype into our final design. So our technical constraints are first is microwave oven arcing or sparking. Any rigid metallic objects in the microwave could possibly destroy our sample or give us results that will not be good for our sample. The temperature of the plasma contained in the quartz reaction chamber will reach very high, so we're going to make sure quartz could withstand this temperature. The access to our substrate in which we are testing needs to be easy access, but also able to seal to the system, as we will be using a vacuum pressure. The purpose of the vacuum is to help initiate the plasma, and also as a safety measure, if the system were to have any problems, it would implode rather than explode from too much pressure. And the gas flow. This is how we'll be creating our temperature. So a steady gas flow is important to keep a consistent temperature. The cost of our project isn't too much of a concern because we are funded by the Temple University Renewables Energy Lab, but we were trying to keep it to a sensible limit in case this project is redone in the future. The power of the tube furnace is 700 watts, so we needed a microwave that had more than this to make sure we could de-wet a sample. We wanted our microwave plasma reactor to be reliable for many years to come, so if many tests were done at the same variables, we would get similar results. The size of a microwave plasma reactor, we'd like to keep it at a benchtop use, so it can be moved throughout the lab, and it also can be moved to other labs if needed. And the safety with the plasma and the microwaves in the MPR, it is important to minimize leakage. So this is the hardware that we will be using. We have the microwave oven, the quartz reaction chamber, the inert gas of argon, our membrane pump, thermocouple gauge, sapphire substrates, and a spark source. So a basic microwave oven has a magnetron and a waveguide. The magnetron is what creates the microwaves. Most of them are located above the microwave cavity, which the potato is located in. Ours will actually have the magnetron and waveguide located on the side of the microwave. This is because we are drilling into the cavity, so this is very important that we don't get leakage of microwaves. Our microwave will have a power rating of 1100 watts compared to the tube furnace, which is rated at 700 watts. This is so we know we'll have enough power to de-wet. And we have a variation of power, so we can vary it at to like 70 or 80% and hopefully get different results controlling our de-wetting sample. Our quartz reaction chamber This will be located inside the microwave cavity. It's important that it contains no metal, so it's non-reactive to the microwaves. As you can see, the cap is now quartz along with the quartz, and then our ceiling is a plexiglass with Teflon screws. If we measure the heat input, if we concentrate the 1100 watts of the microwave for about a minute with the mass of the quartz chamber being about 140 grams and the specific heat around 700 kilojoules per kilogram Celsius, we got about an 800 degree Celsius worst case scenario. Our diaphragm pump, we chose this for a couple reasons. This is the most expensive piece of our project. We mostly chose it for its oil-free design, so if there's any backflow in our gas handling system, it will not contaminate the substrate. It's also very compact. Our thermocouple gauge is important because it can read pressures with argon. Other gauges cannot accurately read the pressures of argon. It reads pressures from 1,000th of a torr to 760 torr, which is important if we get a better pump in the future. So if we get a better pump, it allows for oxygen-sensitive materials such as silver or copper to be de-wetted. So we have test specifications. We have our initial prototype, our final prototype, and our final design. The first test we did was our plexiglass test, was to see if plexiglass successfully blocked UV rays to put in front of our microwave during the plasma reaction. As you can see, the transmission of the light is 100% for visible light and infrared. Once it reaches the ultraviolet light, it goes to 0. In our initial prototype test, we were able to find out that we could indeed make plasma in the microwave. We did find out that we needed a spark source. So from this test, you can see it goes from a red to a blue back to a red again. And this shows uneven temperature distribution throughout, and it was not able to sustain. So this is our advanced prototype. We added the gas handling system above the microwave. You can see the holes drilled through, and our initial quartz reaction chamber. This is our membrane pump and our argon gas well. With this prototype, we were able to sustain plasma. You can play the video. For an indefinite amount of time, we tested for like a minute, just to see if it worked. As you can see, the color remains more consistent. It's normally like a blue. I think it's the projector. But it shows us that the temperature remains constant throughout. Through this, from this prototype, we were able to then de-wet a gold thin film sample. We found out we could sustain the plasma for long periods of time, so this could be used for many sources as plasma etching or plasma cleaning. We had the uniform plasma, which was blue color, which stayed the same throughout, and there was no arcing. This is the validation of our sample that we were able to create. So NWA is a non-de-wetted thin film of gold on a substrate, while MWB is a de-wetted thin film of gold. In this validation process of spectroscopy, we got a peak at 528 nanometers. So this is the wavelength of light. So what happens is 528 is around blue and green for light, and so this is why these are the colors that do not pass through. So once it reaches around 600 and greater, it's red, and this color will be scattered throughout. And that's why the NWB has the characteristic color of pink. And alternatively, the non-de-wetted sample has a peak around 800, which is the red color. Risks of our prototype, we found out the Teflon cap that we were using for our original quartz reaction chamber was showing signs of degradation, so we needed to fix that. We also needed to find a more reliable spark source. So we were using aluminum, and under high temperatures, aluminum could melt or oxidize. Things that we did find out and fix, we have our escaping microwaves. We bought a microwave oven leakage meter, so we were able to measure the microwaves. We stopped most of the microwaves with aluminum and steel pieces above the holes. Escaping UV rays, so we used the UV test and we found out that plexiglass does indeed block the UV rays. And we also bought a shaded acrylic block to block the intense light of the plasma. So this is our final design. As you can see, we re-implemented the gas handling system from the prototype. We have the gauge attached now to measure the pressure, our pump, our tank, and our new quartz reaction chamber in the cavity. So our new quartz reaction chamber will consist of the two pieces of quartz, the Teflon screws and wing nuts, and plexiglass. The idea is that the quartz was able to withstand the temperature, so we were able to create a quartz cap now, and it should keep a sealant with a Viton O-ring. And we would like to create a new spark with the nickel mesh, but if the plasma gets too hot, we would move on to a platinum mesh. So the cost of our project, our quartz reaction chambers are custom pieces, they're about $50. Our membrane pump was our most expensive piece, around $1,850. Our gauge, the thermocouple gauge was around $383. Our microwave was around $86. Our tank to fill is $25, and the miscellaneous connections and fittings cost around $300. This is our schedule update for Senior Design 2. The validation process from the prototype has been pushed down because the SEM and the AFM not working, but we have also moved on to our final design. So to summarize everything, in Senior Design we were able to create our quartz reaction chamber, we acquired our parts for our prototype, and we built the prototype. In Senior Design 2 we then tested the prototype, made new designs for our final design, and then created our final design. Are there any questions?
Yeah, can you explain what is duetting? It's just removing wetness, and what is the importance of it?
Okay, de-wetting, so a thin film on a substrate, I don't think we're going to pictures. If you could think of it as like water on a hydrophobic glass, water would be similar throughout, and then once it were to rest, it would ball up, creating a optical structure of like a sphere. And so heating a thin film makes the a sample of gold ball up into like a de-wet sample.
And what is the purpose of doing it?
It has many purposes in the plasmonic research. So if you go to the graph with the lighting, so this plasmon peak, it has a lot to do with plasmonic activity. So we were able to use certain lights, we would be able to use certain lights through the sample.
And then why do you call the thermocouple gauge the pressure gauge?
Yeah, the torch, I noticed that too.
It's just the way it measures the pressure.
Through a thermocouple?
Yes.
On the inside of the gauge is a thermocouple.
Measure the temperature
Yeah,
and pressure.
for low, it's very good for low pressures.
So it's a thermocouple, but it works under low pressures.
Yes.
Okay.
Dr. Chen, do you have a question?
What did you use to measure the light transmission through the quartz? You mentioned that you can block the UV light. What
it was
did you use?
We used plexiglass for the test, and then we used a spectrophotometer. We went to Bury, the chemistry department, and we cut the plexiglass down to a small piece. So we were able.
100%.
So this is the transmission of the light through.
Yeah.
So the visible light and the infrared light can go through the plexiglass while the UV light is diminished to zero.
It's called what? Spectrometer?
Yes, spectrometer or spectrophotometer.
Spectrophotometer.
Measures the light through the spectrum.
Okay.
Is this your actual results, or is this just a result?
No, this is our actual results. We cut the plexiglass and tested ourselves.
I'm surprised so flat. 100% go through after 400 nanometers. Almost 100%.
That's why it's transparent.
Yeah.
It's a color.
So yeah, that's why you can see that.
That's why we use it in place of glass sometimes.
Yeah.
Those wavelengths.
In the visible wavelengths, it's transparent.
Even
But
for-
beyond the IR, that could change.
Yeah, but even for index or reflection mismatch, there's some absorption there.
Yeah, I would think there'd be some
Right,
fluctuations.
even if with a mismatch of a refraction.
No, it has a band gap, so that's where the band gap is, where the transmission drops to zero.
Yeah.
You said you had some leakage around the holes which you blocked with foil, but then when you found a picture, prototype picture, you had
No, we didn't use foil. So as you can see, you can't really see in this picture, but there are steel washers. So there's the aluminum hold of our apparatus of the gas handling system, and then there are steel washers above that. So we have two pieces there.
And are you using like Teflon screws to
Yes.
hold stick?
Yeah,
Pieces
Teflon.
together?
Yeah, Teflon.